Okay, so this is a tangential. The previous part was a supplemental. So supplemental means it is something that I wish I could tell you, but I don't have the time. So it's like, if you want to watch it, watch it. If not, it's fine. It's a useful stuff, but it's up to you. Tangential is even less important. It's something that I find interesting and is very tangentially related to the course material. I'm happy to tell you about it, but you don't need to hear it. You don't need to listen to it. It wouldn't help you in life. So, say it if you're interested, because I find it interesting, or don't. It's completely up to you. I'm just recording it because I find this stuff fun, so I think it's worth my time. But it's up to you to decide whether it's worth your time or not. Okay, so I wanted to tell you a little bit more about Fibonacci and Fibonacci numbers. So Fibonacci was born in 1170, and he was Italian, and he spent a lot of time in the Levant because he was the son of a merchant, Italian merchant that traded all over the Middle East, Algeria, Tunisia, and so on. And during his travel in those areas, growing up, he learned the Hindu-Arabic numeral system, right? The digits, the digital and the place-based system that we currently use. Before that, Europe used, God forbids, Roman numerals. And by the way they would multiply numbers was using the Egyptian multiplication algorithm that he spoke about earlier. Now, the Hindu Arabic numerals are quite interesting on their own. So they were developed somewhere around 400 CE or before that by some Hindu philosophers or thinkers, whatever you want to call them. We know that it arrived to the Arab world sometime before 825 because Muhammad ibn Musa al-Khuzrimi wrote a book explaining the system. And by the way, this guy also showed how to solve quadratic equations. So he came up with the quadratic equation system we currently know, the current formula. And in his book, he describes how to, as I said, he described this numeral system. He also, by the way, is the source for two important things in the language. So the word algorithm is derived from his name somehow, and the word algebra is coming from is the title of his book. And because he's in some sense the first one, my understanding, that started using our variables notations when he wrote about solve the quadratic equation and so on. Okay, so in 1200 roughly, Fibonacci wrote a book, Liber Abaci, which is the book of calculation, where he explained the digital system and the Arabic numeral system. And he was in Italy, and it was, it became an extremely popular book. And that's how the idea arrived to Europe, right? Okay. So this is, by the way, I should say, this is amazing because it's kind of amazing that we know how this really important idea, right, of this numeral system that had such a fundamental contribution. We know exactly how this idea spread in the world, right? We know when it arrived roughly to the Arab world. We know when it arrived from the Arab world to Europe by Fibonacci. And we know the two people that were the main spreaders of the idea, which is kind of interesting. It also tells you something very interesting, that those ideas are very simple, but they are very old. They're old, but in some sense they're not that old, in the sense that they are, Greeks were doing geometry 1,000 years before that, or even 1,500 before that. And it took a long while to come up with the right, with the current numeral system. So it's kind of impressive. Okay, which also tell you that simple ideas sometimes is very simple, but they're very, very difficult to find and come up with. Okay, now let's go back to Fibonacci numbers. He wrote in this book that I mentioned earlier, he had a problem about how rabbits multiply, right? And so the basic idea that you have a mature pair of rabbits and they give birth to a new pair of rabbits every month. This pair of rabbits are young, so you have to wait a month before they become mature. Once they are mature, every month they give birth to one pair of rabbits, right? So, and the question is, how many mature pairs of rabbits do you have at any given point in time, right? So in the beginning, you have one grown-up pair of, look on this table, we have one pair of rabbits. A month later, this grown-up pair of rabbits give birth to one pair of rabbits. And of course, they are still grown up. So this is the situation. We have two pairs of rabbits, one young, one old. The next month, the mature pairs is going to give one new pair. This young pair is now mature, right? So the number of mature pairs is the sum of those two numbers, right? And we repeat in this fashion, right? The number of young pairs is always copied from the number of mature pairs in the previous month because every one of them give birth to one mature pairs. And the number of grown-up pairs at the month is the sum of the young pairs and grown-up pairs in the previous month. So what you get is the Fibonacci sequence. Okay. By the way, this sounds ridiculous, right? Because it's exponential growth. But there's at least one case that this happened, in the sense that when Australia, people brought rabbits to Australia, they grew exponentially. I don't know if they quite followed the Fibonacci sequence, but whatever they followed, they grew to crazy numbers. And across Australia, they built a fence called to block the rabbits from moving from one part to another. There is a very nice movie called Rabbit Proof Fence, which I recommend to see if you want, which is completely has nothing to do with rabbits, but it's just a very good movie, essentially involving two kids walking along this fence for thousands of kilometers. It's really an amazing movie. Okay, so this is the problem that he came up with, and it's kind of amazing that we remember his numbers, but his important contribution was bringing the Hindu-Arabic numeral system to Europe, which is much more important than this silly sequence. Now, I should say that people care about Fibonacci numbers because there are a lot of nice things about them. So one nice thing about Fibonacci numbers is that they converge to the golden ratio, right? So if you look on this, the ratio, it converts to this ratio. This ratio was defined by Euclid, so it's pretty old. The basic idea is that you take two intervals, one of length A, one of length B, and A is larger than B. And now you ask, what's the ratio of the two segments put together, right? So AB over A, the two segments together over the first segment, the length. You want this ratio to be the same as the ratio between A and B, right? So this is a natural, question. You can write this down as an equation, right? You have this ratio and you want it to be equal to this and this. And then if you solve this equation, you get this relation. You get this quadratic equation. Now, using the formula that Kuzerami came up with, we know what's the root of this, two roots of this quadratic equations. Since the ratio cannot be negative, we take only the positive ratio, and we get this golden ratio, right? And people care about golden ratio because because they believe somehow it's pleasing. So there are some famous paintings that have the golden ratio. The golden ratio appears in several places in nature. There's some claim that it appears in music. You can take those. You should take some of those claims with a grain of salt or 2 grains of salt. Fibonacci sequences, on the other hand, they describe a growth process which is natural, and people like to use it in the stock market, in analyzing sequences in the stock market. My feeling is that some of it is a bit of mumbo jumbo, but people use it, so good for them. Okay, so one of the cool things about Fibonacci number is that there is a closed formula for the nth Fibonacci number. You don't need to compute the recurrence. So this is called Binet's formula, and the proof is not difficult, so I thought I would just show you the proof because it's kind of cute. You might have seen it before in a math class, although I doubt it. So we have the 2 roots of our quadratic equations, right? Phi and psi, right? +1, -1. And the important thing is that phi and psi are also solving the general equation x of n is equal to xn minus 1 plus xn minus 2. Why is this true? Well, all I did was to take these quadratic equations and multiply it by xn minus 2, right? So this is definitely true, and this definitely looks like, this recurrence looks really very much like a Fibonacci sequence, right? So in particular, consider a sequence that look like a Fibonacci sequence, right? Un is equal to un minus 1 plus un minus 2. And for every number alpha and beta, consider the sequence, the sequence where we put un equal to alpha time phi of n plus beta time of psi of n, right? This is a valid solution to the sequence. So one needs to verify it, but that's not very difficult. So, you just write down the recurrence, you open it up, you rearrange, right? You get alpha of phi n minus 1 plus alpha of, that should be psi. Sorry, this is a typo. Okay, that's what happened when you just copy. Let's be careful about it. Yeah, so this is this. This is E. Now I'm confused. Let me try to do it again. You take this element, you take this element, right? So you get this. This is fine, right? And then you take this one, and you get this one. Okay, yes. So you just rearrange the element like that. And now you can take the alpha out from here, right? And we indeed get, this is just un minus 1. By definition, this is un minus 2. Right? So indeed we get that un is equal to un minus 1 plus un minus 2 under this choice. So what is going on here? What's going on here is that we found a family of possible solutions, right? For every value of alpha and beta, we get a valid solution to this recurrence that looks like a Fibonacci, right? Now this recurrence is determined by the first 2 elements in the recurrence, right? So if I want to get the specific Fibonacci sequence, all I need is to enforce the condition that u0 is equal to 0 and u1 is equal to 1, which translate into those 2 equations, right? That on alpha and beta, which are linear equations in alpha and beta, and we can just solve them, right? So let's just do that. That's not especially hard or difficult. And we get that alpha is equal to 1 over square root 5, and beta is equal to minus alpha, and putting it in, we get the Binet formula, which is this one. So QED, which I thought was very easy and clean, so I thought it was worth showing. Okay. Now, the last thing I want to mention is that you can compute Fibonacci number really, really fast, which looks very weird. So the basic idea is that you can write Fibonacci number using matrix form, right? So the idea is that fn minus 1 fn is equal to fn minus 1 fn minus 2 and fn minus 1 when you multiply it by this matrix, right? So it's easy to see that this is correct, right? The first row just takes the bottom element and make it the top element, and the second row takes the two previous elements and just add them up and give you fn. So in particular, we get that we can compute the nth Fibonacci number by computing this matrix to the power of n minus 1. Okay, so what's the big deal? So the big deal is that if I want to compute a to the n, naively this takes O of n time, right? I have to multiply a by itself n time, but in fact you can do it much faster, right? Because you can do what is called fast exponentiation, where fast exponentiation just use the following observation. If you have a to the power 2k, you can write it as a to the k squared, right? If on the other hand you have something that is 2k plus 1, then you can write it as a times a to the 2k, right? Or if you want to be even more efficient, we can just write it directly as such, right? So in either case, you reduce the problem from n to be of size n over 2, right? You do one recursive call when you compute a to the 2k or a to the n. You're doing one recursive call, a to the 2k. When you do one recursive call, and the recursive call is in half the value, right? So the depth of the recursion is going to be of log n. You're doing only one recursive call, so the overall running time is going to be log n. So that implies that you can do the exponentiation in log n time. And this is a matrix of size 2 by 2, so the same algorithm works. You have to look at it carefully for a second, but it works. So you can compute this power of this matrix in O of log n time, so which means that you can compute the n Fibonacci number in log n time. Now, of course, there are a lot of technical problems here because the numbers are huge, right? And in particular, just multiplying the n Fibonacci number have n digits, multiplying two numbers take quadratic time, at least with a naive algorithm. So this doesn't really improve things, right? But as I mentioned earlier on, we know how to multiply two n-bit number in, let's say, n log square n time, right? So if you are going to use this super fast multiplication algorithm, which we didn't cover, but it's known, together with the fact that we can do this fast exponentiation using log n multiplication, we will get an algorithm for computing the n Fibonacci number in n log cubed n number, which is a big improvement of our previous algorithm, which was, of course, quadratic time, right? So this is how you can do fast exponentiation. Of course, if you're ignoring the bit issue, we get an algorithm that runs in log n time, which is, of course, a dramatic improvement over the previous algorithm. But in this case, you have to worry about the size of the numbers. So it's not quite, it's kind of cheating to ignore the size of the number when you speak about Fibonacci numbers. Okay. Okay, so that's it. That's all I wanted to tell you.